So we just have just a little bit more to sort of finish up here in this chapter, which I believe is 10, I think we're on. So last time we talked about really colligative properties, and we talked about a few different things. We talked about vapor pressure lowering, where you got P is equal to X of A and P naught of A. And we also talked about freezing point depression, and also boiling point elevation. And really, all these are related to colligative properties, and they're really based on the number of particles that are in a solution. So what happens, as we talked about, is instead of just having, say, a pure liquid like a solvent present, where there's really nothing there other than solvent molecules, um, when it goes to boil, when it goes to freeze, when it tries to escape into the gas phase, there's really not too much in its way. But once we kind of make a solution and we really dissolve any type of solute in here, we end up with both the solvent molecules in that solution, and now we have other particles. I'll just make those blue circles. And the presence of these sort of solute molecules in the solution, it kind of disrupts the natural process of things like it boiling at its boiling point, it coming together to freeze at its normal freezing point. It affects things like the vapor pressure because, again, there's a lot more stuff in the way. It's going to allow perhaps less molecules escaping the liquid and making less vapor over liquid, and we get these vapor pressure lowering. So, we have vapor pressure lowering. This is the pressure of really the component in the solution. That is its mole fraction, and that is the basically the vapor pressure of just the pure liquid by itself or solvent by itself. For freezing point depression and boiling point depression, we had a couple of equations that kind of look very similar. The change in freezing point temperature is equal to the Kf times m. This again is the change in freezing point temperature. And as we did in a couple of examples, again, that is not the temperature at which that solution freezes, but that is the change in degrees Celsius of where it will freeze. So for example, if we were talking the comparison of water to like sodium chloride solution that has dissolved in it, um, it will actually freeze below zero, whatever that change in temperature is. Kf is the freezing point constant. And remember that that is something that you can look up on a table. And again, the freezing point constant, though, is based on the solvent. So it is not based on the solution. So sometimes people go to that table and go, I can't find like the solution listed. It is based on what the solvent is. So if you're dealing with something that is aqueous or something like that, probably the solvent is water. It may not always be water though, so it can vary. That's also really important too, because if it is water, we use 0 degrees Celsius for the freezing point of it where it normally occurs. But obviously, if the solvent's not water, then that substance may actually have a different freezing point, and you would not want to use zero. So you would want to use the appropriate freezing point temperature for whatever that solvent may be. M is our molality, which again is our moles over kilograms of solvent. And we have a boiling point sort of one as well that's very similar. The change in the boiling point temperature is Kb times m. Once again here, this is, as I just mentioned, the change in the boiling point temperature. The Kb is the boiling point constant, also based off of the solvent. And m here is our molality, which again is our moles per kilogram. Remember that there is sort of an important relationship in terms of the change part of this, which is if you're doing the change in freezing point temperature, that would be the temperature at which the solvent normally freezes minus the temperature of the solution. And that's because the solvent will actually be a higher temperature where it freezes than the solution will be. And that is different than when you're doing the change in the boiling point temperature. Because it is boiling point elevation, the solution will actually boil at a higher temperature than the pure solvent. So in this case, we actually take the temperature of the solution minus the temperature of the solvent. And those two relationships are really important because it will allow you to either multiply, add or subtract correctly, depending on what you're looking for, if you do it in that sort of direction. We also talked about vapor pressure, which we did. We also talked about osmotic pressure. Osmotic pressure is, again, the pressure of basically coming back down on a natural process of osmosis. So if you have some type of membrane there that allows the flow of certain size molecules, and you have just, say, pure water on the left and like salt water, as we talked about there, on the right of the membrane, the process of osmosis basically means that the solvent water molecules will flow from a lower concentration to a higher concentration. And again, it will continue to flow until it hits basically what's known as the osmotic pressure. And that's the pressure that will stop basically that flow of solvent molecules across the membrane, because now there's pressure pushing basically back down on it. We can calculate this with a fancy looking formula, which is pi is equal to nRT over V. But really, it's, the ideal gas law in disguise, basically. So it is just the ideal gas law as we talked about. And you could use it just like the ideal gas law. You do want to make sure, like we've talked about previously, that everybody's in the correct units. So again, here, atmospheres for pressure, moles, temperature, Kelvin, volume, liters. And you could just solve straight up for the osmotic pressure this way. You could also do a couple of examples like we did, where you could use it to calculate something like molar mass as well. You could also use boiling point and freezing point information to also do something like that, calculate molar mass and stuff of that nature. Now, we finished up talking about these sort of colligative properties, and really everything that we see on the screen that we talked about at the beginning was all when we have a solute sort of molecules that were dissolved in it, which were non-ionic and non-volatile, they're sometimes referred to. So they basically just stay together when they go for a swim. They don't break apart into multiple particles when they do that. So when we do have something like that, which is non-ionic, and it does go for a swim, when it goes in there, we basically get a 1-to-1 relationship in terms of how many particles go into swim around in the swimming pool. And when we have something that's ionic, it is different because it's going to break apart actually into its ions, because it's a strong electrolyte. So again, if you have something like sodium chloride, when that goes for a swim, you're going to get some sodium ions and chloride ions. You're basically going to get, for every one of these, kind of a twofold sort of number of particles. And since these colligative properties are based on the number of particles that are present, that's going to affect things like the freezing point, the boiling point, the vapor pressure as well, by the way, and all those other guys. So, if you had something like, I think we looked at calcium chloride as well, when that goes in, you'll get a calcium ion and two chloride ions floating around. That's basically a 1-to-3 relationship that you're going to get. So this is what's referred to as the von Hoff factor, which is the I. And we do need to incorporate sort of the I into those calculations when we're dealing with something that's ionic. And you could do it based really off the formula in most cases. Again, if it was something like sodium chloride, I would be 2. If it was something like calcium chloride, I would be 3. As we talked about, the reason we didn't actually incorporate that in those earlier examples that we did was because we were using something that was non-volatile or non-ionic, which means basically I was 1. So for every molecule that went in, you basically got 1 out. And so we don't really need to multiply it by 1. It's going to come out the same. So that's why they're not incorporated into those formulas earlier on that we did. But again, if you're doing anything that's ionic, you do need to incorporate that in. And it's really kind of the same formulas. The only addition is you insert that I there into the calculation. Everything else is basically the same. You insert that I into that place. You could also deal with the vapor pressure. Usually if you deal with the vapor pressure, where the eye actually gets inserted in is actually in the mole fraction part, and it's actually usually on the bottom part of it, um, because when you do your mole fraction, you got your moles of whatever you're interested in divided by usually like the solvent moles and the solute moles. So usually right around here is where you would kind of incorporate I. If you're doing something that was the vapor pressure sort of part of it, you wouldn't necessarily put it right in front, like in the formula and stuff like that. You just really have to multiply the moles of the solute by that I factor. Is really where that sort of comes into play if you're doing something like vapor pressure lowering. Any questions on any of that stuff there? Yeah. Oh, it's possible. I mean, it could be, for example, if you had anything that was, say, ionic, if you had, I don't know, probably a bad example, but we do something like rust or something like that, iron 2 oxide here, then obviously I would be 3 in that case or something like that. That would be more of a solid, but it's possible it could be more than 3. It's really just based on the formula there and how it would break apart. Yeah. Other questions? All right, so to finish up the last little bit here on this chapter in solutions, we're talking some more about the properties of solutions. As we talked about before, a semi-pyramidal membrane basically allows certain size molecules to flow back and forth, like our cell membranes. But essentially, in these type of membranes, they basically have holes in it, and like I said, that's big enough for certain size things to kind of sail through with no problem. But again, if you get something a little bit bigger, it is going to have a little bit of an issue fitting through that hole. And when we talk about sort of solutions, there are things known as colloids, and colloids are much larger than solute particles in a solution. These are large molecules like proteins that are grouped together, or groups of molecules or ions. Colloids, though, are homogeneous, which means they all look the same throughout. It's a mixture. They do not settle out because of that, because everything's mixed together and it's a homogeneous mixture. They are small enough to pass through filters, and filters here like filter paper, like on a funnel. So if you put some filter paper there on a funnel, those guys are small enough to go through there. Um, but they're too large to pass through a semi-pyramidal membrane. Another type of classification is a suspension, and a suspension is a heterogeneous mixture. And heterogeneous means you do see different phases when you look at it. And these are often really large enough that you could kind of see the different size particles there with your naked eye. So, for example, if you took like some sand and threw it in water, you definitely could see the sand in the water. It's big enough, right? And that would be a suspension. They are also trapped both by filters and membranes. They basically don't go through anything because they're quite large. So, same idea. If you were going to take that sandy water and put it through a filter, your sand's not going to go through the filter paper, right? It's going to get stuck on it, so it won't be able to go through there. And it definitely wouldn't be able to go through any type of membrane as well. Here's sort of a zoomed in version of a membrane. And again, although you oftentimes can't see the holes, there are holes that basically allow passage of certain size molecules. Again, larger guys, are going to have some trouble passing through that. And you can see really on this side here, as they're flowing through, not a lot of big molecules have made it from the left-hand side to the right-hand side because it gets trapped. Here's just a picture we are just talking about. So suspensions, they do settle out. Again, like if you have sand and water, it's going to settle to the bottom of the beaker, right? Solution colloids will still be floating around. Our solution colloids will go through filter paper with our suspension getting caught. And really only those small sort of solution molecules will go through a membrane, like a dialysis bag, for example, that allows those guys to go through. So we talked a little bit about this, which is osmosis and dialysis. And again, osmosis is the sort of process where really it's an idea to try to dilute down one side of, say, a membrane from another. And the idea is one side is more concentrated and the other side is less concentrated. So it always flows from the least concentrated to the more concentrated side. And that is the flow that happens there in an effort to really dilute down the more concentrated side of it. Now, osmotic pressure, as we talked about, basically, as we just said, there is really that pressure that's reached as this process is occurring. And that will, again, really stop the flow, for example, of our water molecules to this side. It will reach the osmotic pressure. As I mentioned, yeah, last time, you could apply a force greater than the osmotic pressure, and that would push back down the other way. And that would send all the water molecules basically back the other way. And if you had good filters and stuff like that, you could catch everything that you didn't want to go through that. That is what is referred to sometimes, again, as reverse osmosis, is kind of pushing everything back the other way using a greater pressure. Now, the greater number of molecules basically dissolved in a solution, the greater the osmotic pressure. You could calculate the osmotic pressure, obviously, using the ideal gas law. Sometimes another unit is sometimes used, which is known as osmolarity, to indicate basically osmotic pressure. So osmol is sometimes referred to, or osmolarity, basically. And it really is calculated by taking I times M, which is the molarity. So basically the von Hoff factor times the molarity. So if you took something like a 2-molar sodium chloride solution versus a 2-molar calcium chloride solution, when you would go calculate the osmolarity of each of these, as we talked about before, I in this case would equal 2 for our sodium chloride. So the osmolarity here for our sodium chloride solution would be 2 times our 2 molar, and that would give us basically 4 osmolarity. And if we do the same calculation here for our calcium chloride, where I is equal to 3, that would give us an osmolarity for our calcium chloride of 3 times our 2 molar. And that's going to give us 6 osmolarity. Because there's more particles, again, in the calcium chloride here, it actually has a higher osmolarity and also a greater osmotic pressure because of the number of particles that are in there. If you had 1 molar of a sort of non-ionic, it would just be obviously 2 osmolarity, as I would equal 1 in that case. Pure water has no osmotic pressure because it has nothing dissolved in it. It's just water molecules together. It's basically just a pure solvent at that point. So there's nothing dissolved in there, and it has really no osmotic pressure. That is why in the diagram up here, water is flowing through osmosis to the more concentrated side because it has less osmotic pressure to the higher osmotic pressure, which would be like the salt water. Any questions on that there? And that's what we see here again, brine, which is basically salt water and water. We're going to get a flow of the water to the way more concentrated solution over there in an effort to dilute it. And again, if we apply pressure backwards to do some reverse osmosis, we could push everybody back the other way and get that pure water. Now, this brings us to 3 ways to classify solutions, and that is isotonic, hypotonic, and hypertonic. And isotonic solutions exert the same osmotic pressure as body fluids. And most IV bags and solutions are isotonic. So what does that mean? It means, for example, if we took like a red blood cell, which is the classic example of this thing, and we drop it into a isotonic solution, because the osmotic pressure inside the cell and outside the cell is basically equal to each other, what we end up getting is nice equal kind of flow in and out of the cell. So nice equal kind of flow back and forth as it's basically pressurized on both sides as the same. The cell, right, is like a membrane, right? It allows things to flow in and flow out of the cell, for example. What are considered isotonic solutions? So most of the time that is a 0.9% mass to volume sodium chloride solution, or sometimes referred to as a saline solution. It doesn't have to be sodium chloride. It could be any type of ionic guy like that. And are a 5% by mass glucose or sugar solution. These are considered isotonic solutions. And anything that is above it or below those two guys would be not isotonic. It would be one of the following types of solutions. One of those is a hypotonic solution. Hypo means less than. So if you have a solution that is less than 0.9% sodium chloride or less than 5% glucose, you have a hypotonic solution. What that means is outside of the cell is actually less concentrated than inside the cell. And that is a little bit of a problem because if you take our red blood cell here and you pop it into a hypotonic solution, because outside of the cell is less concentrated than inside, osmosis is going to kick in. And what's going to happen is outside of the cell is going to decide the cell is way too concentrated. So all of the outside solution that's hypotonic is going to rush into the cell in an effort to dilute down basically the cell's concentration. The result of that is if all the water runs into the cell is going to start to swell and can possibly burst, which is known as hemolysis, which is probably not a good thing, I imagine. So not so good. And you'll get that sort of process occurring. Now, if we have a hypertonic solution, hyper means more than. So if you have a solution that is greater than 0.9% sodium chloride or greater than 5% glucose, that is a hypertonic solution. That also is not the greatest situation, say for a red blood cell. And that is because in this particular case, the solution outside of the cell is actually more concentrated than inside the cell. So what's going to happen is osmosis again. And in this case, all of the fluid from the cell is going to go, I'm going to go dilute down that solution. So all this solution or the fluid in the cell is going to run out of the cell in an effort to dilute down the solution that's outside of it. The result of that is you're going to get a cell that's going to start to shrink because it's basically dehydrating itself. It's losing all its sort of solution. And that is what's known as crenation. Also, not a great deal, right? That is why, again, IV solutions are isotonic because if you're getting an IV, you're probably not in the best of shape or something's not so great for you. So you don't want to screw everybody up more by giving either a hypotonic or a hypertonic type solution to somebody. Any questions on that there? And here's some pictures of that. So if we have an isotonic solution, I call it the regular donut. If we have a hypertonic solution, you get the donut hole. And if we have the hypotonic solution, we get the jelly donut as it bursts out all over the place. So why don't you decide what will happen here? Will it be okay? Will it shrink? Will it burst? If we put a red blood cell in the following solutions, let's go with 2% sodium chloride. Let's go with 3% glucose. Let's go with good old pure water. And let's go with 0.9% sodium chloride. All right, so for each of them, decide what will happen. Okay, so let's take a look. So again, to make that decision, you should know that isotonic again is 0.9% sodium chloride and 5% glucose. So when we look at our guy over here, which is 2% sodium chloride, that is definitely higher than 0.9. That means that this is a hypertonic solution, greater than osmotic pressure. That means outside of the cell is a greater osmotic pressure than inside the cell, and that should cause all of the fluid in the cell basically to rush out of it, and that would get us basically some shrinking going on there, which is crenation. Any questions on that one there? If we go with 3% glucose, 3% is less than 5%. That means that this is going to be a hypotonic solution. And hypotonic means in this case that outside of the cell is less concentrated than inside the cell. That's going to cause all the solution outside the cell to rush into the cell. going to cause the cell to start to swell and burst, probably, which is known as hemolysis, burst and swell, basically. Any question on those two? 0.9% sodium chloride is 0.9%. So that is an isotonic solution. That's going to be all okay. We're going to get nice equal flowing in and out of the cell. Our cell is going to be okay. How about if I put it in pure water? Will it be okay? The answer is this is a case where pure water is not okay because pure water has no osmotic pressure, which means that it actually is a hypotonic solution. And that means that outside of the cell is actually less concentrated than inside the cell. So we're going to have everybody flowing into the cell, and that's going to burst and swell. Any questions on any of those things there? Okay. Now, dialysis is a process similar to osmosis. It does allow certain size molecules to pass in and out, say, of a dialysis bag in our body, right? We get rid of some waste products through that way in our kidneys and such to dialyze things out. And in the laboratory, we sometimes will use a dialysis bag. For example, if you're doing some type of experiment on a protein and you want it in a particular environment, like a particular pH environment. What you can do is just make a buffer that has a specific pH solution. You can slap your protein in the bag and drop it in there. And because the protein is too big to get out of the bag, it will stay in there and it will basically equalize to the same sort of environment, say maybe in the body or something like that. So sometimes people will use dialysis to do things like that to sort of incubate something like that. Obviously, like I said, in the body, we kind of get rid of some products that we don't want. And if you have trouble doing that, you need to go for dialysis to have that done for you. So here's that example again. Although if you look at a dialysis bag, you won't be able to see the holes. But again, there's small holes that allow just the small guys basically to escape. Larger particles going to be trapped inside. All right, any questions on that there? That wraps up this chapter. And we will go off to the final one of the season here. So this is the final chapter of the year. That's good. This is not on the exam coming up on Tuesday. Obviously, what we just finished is the last material that will be on the exam on Tuesday, which again is, I believe, chapter 9 and 10, right? So whatever was in those chapters. So chemical kinetics is about really how fast, for example, or slow a reaction takes place. That is sort of what kinetics deals with. And it shouldn't be confused with thermodynamics, which we don't talk about at all in this class anymore. But if you're going on 200B, you'll talk all about thermodynamics, including energy. You'll talk about entropy, and you'll talk about Gibbs free energy as well. And these are thermodynamic sort of properties. And as you'll learn, delta H really, which is enthalpy. What thermodynamics actually deals with, most of it or a lot of it, is the idea of spontaneous type reactions. And is a reaction spontaneous? And sometimes people have a really misunderstanding about thermodynamics when they study it, because they think if a reaction, for example, is spontaneous, they think that it occurs always like snap your fingers super fast. And that's not really what the definition of spontaneous really means in terms of thermodynamics. What it means is under those conditions, basically, that reaction should take place is basically what spontaneous means. Now, that reaction could take place really fast, or that reaction could take all day to take place, but it will eventually take place if you leave it long enough. So spontaneity in terms of reactions, and when we say reaction spontaneous, it doesn't necessarily mean anything to do with how fast or slow. That area of sort of chemistry is what kinetics deals with. Kinetics deals with how fast or how slow, for example, a reaction takes place. So let's talk a little bit about reactions. A couple of ways that we can sort of indicate how fast or slow a reaction takes place. So a lot of times we look at what is referred to as the reaction rate, and that is oftentimes the change in the concentration of a reactant or product over time. And common units of that is, since molarity is the most common unit that we deal with, we oftentimes look at how the molarity is changing per unit of time, are seconds. Now, the time doesn't always have to be seconds. It can be minutes, hours, days, weeks, years. But most of the time, if you're doing some type of experiment, a lot of times you measure how long it took, like in seconds. So it's a very common unit of it. When we look at a reaction like this simple one here of A going to B, we have our reactants going to our products, which means in this reaction, as time goes on, we should be converting our reactants into products, which means the amount of reactants that we start with should start decreasing with time, and the amount of products that we are making should be increasing with time. So as time goes on, the amount of A should be going down, and the amount of B should be actually increasing because we're making more products. So we could write what is sometimes referred to as the rate expression, which are these guys basically down here. And we could say that the rate is equal to negative the change in the concentration of A over the change in time. So what does that mean? That delta is the change, concentration is molarity, so that's like your final molarity minus your initial molarity, like final minus initial, right? Change in time, same deal. That's your final time, right? Minus your initial time, basically, how much time you took. Now, because this is a reactant and is decreasing with time, we do include a negative in this expression, and the negative is because it's a reactant and it's decreasing with time. That is because when we calculate the rate of a reaction, it is typically a positive number. So we want it to be typically a positive number. So if you think about this reaction just in general, we went from A to B, and initially, let's just say we had 4 of A and nothing of B. And when we were done with this reaction at the end, let's just say we had 1 of A and like 3 of B. And if we were going to calculate, for example, the change in the concentration of A in my made up, and say these are molarities, in my made up example here, we would take our final concentration, which is 1 molar, minus our initial concentration, which is 4 molar, and that would actually give me a negative 3 molar. And that negative that you would get when you do final minus initial, along with this negative here, will turn your rate into a positive number, which is, again, what you want it to be. Now, that is different when we get to B, which is our products. It should be increasing with time. So we have a rate expression here of the rate is equal to the change in the concentration of B over the change in time. Here we do not have a negative. And the reason we do not have a negative here is it's actually increasing with time, our products. So if you take our same example here and we did the change in the concentration of B, it would be our final concentration, which is 3 molar, minus our initial, which is 0. That gives us a positive 3 molar, so we don't need that extra negative sign there. So when we're dealing with reactants, we do not put the negative, so we do put the negative with reactants, but we do not put it with products as it's increasing with time. Any questions on that there? Now, how do we follow, for example, what's going on? Well, there's multiple ways, but if we just graphically look at it here, we are starting with pretty much all reactants at this point. At the beginning of the reaction, there's no red circles there to indicate our products. As time goes on, we start getting some red circles. That means we're making products. We also see the disappearance of some of the black circles, which means we're losing some reactants here until the reaction is kind of over. Kinetics, they love graphs in kinetics. So here we see the same thing at time 0, pretty much no products. all reactants. And as we start using our reactants, we will be making our products. And we will continue to use up our reactants, continue to make products until the reaction is essentially over, or almost all of the reactants have been converted to products. Now, how can we follow what's going on in terms of concentration? We could do a very simple sort of experiment, especially if the reaction that you're following has some type of color involved. So maybe a reactant has a color, or maybe a product has some type of color. In this particular case, this guy actually, a reactant, has the color. It's kind of that orangey type red color that you see in the picture. When we get to the product side, these are all actually colorless. And you can see as this reaction goes over time, our color is starting to go away. And that's because we're converting our Br2 here into products which are colorless. So the solution continues to get light until pretty much there is no color left, which means essentially you probably converted all the reactants you're going to into products. And obviously we don't have very much, if any, reactants left over at this time. Now, how can we actually follow that to get numbers? Well, we could do something known as spectrophotometry, like we did with our Kool-Aid experiment in that Spec 20 sort of thing when we did the Kool-Aid. Remember that when you do that, you do want to choose the wavelength of maximum absorbance. And that's like what we did in the Kool-Aid experiment. We did that because when we take our measurements, we're going to be good. We're going to have basically all of our measurements going to be on the scale. Remember that if you choose down here, good luck. You have like no absorbance value that's going to work. We also know from that experiment and what we talked about, right? The color we see is actually complementary, right, to the color that's being absorbed, right? So when we see our red color that we did in our Kool-Aid, we did not set the wavelength to the red wavelength there. It was more in that kind of greenish bluish area in terms of where it ended up. So how it works, right, is we shoot light at a specific wavelength. It goes through our sample, goes to our detector, and we measure either absorbance or transmittance, percent transmittance. Most of the time we do absorbance. And the change in the concentration, for example, of our species that has a color associated with it is proportional to the change in absorbance. And that's what that little symbol is, the proportional symbol there. The darker the color, the more absorbance we're going to have. And obviously over here, we're not going to get any absorbance, probably zero, because that's colorless, right? So this thing only works with things that have color. This type of measurement here would be frankly useless if we were having a reaction that all the reactants were colorless and all the products were colorless. You're not going to be able to get any type of absorbance information. You could use that in our friend Beer's law, A is equal to BC, or they use ABC here, I think. One of those ones they use here. But you could use something like Beer's law to convert your absorbance values that you would measure into concentration values. So actually how you would do this is you would set this reaction to start, and basically you would just take absorbance values like every second, 5 seconds. You could do every second these days because computers will do it for you. So every second you could take an absorbance reading until basically there is no more absorbance in this case, right? When you would hit like a flat line of absorbance, you pretty much made all products as there's no longer any colors to be absorbed. And you would have high absorbance coming down to low absorbance in that. And you would have a graph that would look something like this. If this was absorbance versus time, you would probably start out with a lot of absorbance, and eventually it would probably flatline out once all the products are made and we have nothing with color left. Again, you could use something like the slope of this line and something like that to calculate something like Beer's constant. And you can use that, like I said, to convert all those absorbance values into concentration. And what you'll have is now concentration versus time values by doing so. So that's a very common way to do a kinetics experiment. And when we do experiments like this, there's usually two types of rates that we talk about. One's the average rate, which is typically what we look at. and one's the instantaneous rate. And the instantaneous rate is for a specific period of time. And the average rate is basically how the reaction is going over the entire period of time. You could think of it as you're driving, right? As you're driving from here to, say, Arizona, perhaps you're doing at some points along your trip 55, 60, 65, 70, 75 for sure when you get into Arizona, maybe 80, 85, maybe not too fast, that fast, hopefully. But anywhere along the way, maybe from your entire trip from beginning to end, your average miles per hour you were driving was maybe 72. But along the way, you might have had pockets of time where you were doing 80, 85, or 50. Maybe you're going slower, right? Or 45 or 55. So for that instantaneous period of time, your rate might have not have matched what the rate was going on over the entire sort of reaction, for example, or your drive. You could calculate the instantaneous rate by taking the slope of the tangent line. Sounds like a lot of math there. And calculate basically your instantaneous rate for a specific period of time. Usually, most of the time, we do go for our average rate, which is kind of from our final to our initial in a chemical reaction, and obviously our final time minus our initial time. This, again, average rate is typically a positive number, is typically what you want for that guy when you do it. And if you look at, say, this reaction that was in that equation, you can do some graph work, and you could also find a relationship where there is sort of a constant value that occurs. And that is not the rate here. As you can see, the sort of instantaneous rate there for different periods of time are different. But there is a relationship if you take something like this, which is we'll talk about shortly. This is what is considered the rate law. And this little k here, and I'll draw dramatic drawing of little k here. Not to be confused with capital K, which is basically what Chem 200B is brought to you by, which is the equilibrium constant. That's the equilibrium constant. So not that, it is this guy, which is known as the rate constant. And a rate constant implies that it is a constant value for that particular reaction. And that's what's here in this column of the table. And you can see pretty much it's the same number all the way through. So there is a relationship that's known as the rate constant. It also gives you sort of how fast or slow the reaction is taking place. So usually if you have a larger rate constant, the reaction is a little bit faster. If you have a lower rate constant, then it's a little bit slower of a reaction. But it is a constant value for a particular reaction based on those conditions. Now, what happens if you do have a reaction that does not have any type of color? And obviously, you couldn't do any of that like Spec 20 type of experiment. So in this case, really all these guys are colorless here, and there really is no sort of color other than the yellow they put in there, so you can actually see it in the picture. But in this case, we could do something like, because this reaction generated a gas, we could actually follow the pressure over time, and that will get us to the concentration over time. And we could do that by using our ideal gas law, which is our PV equals nRT, which we know that is atmospheres, that is liters, that is moles. That obviously is our gas constant and our temperature in Kelvin. And if we solve for P is equal to N over V RT and rearrange it for N over V is equal to P over RT, N is moles and V is liters over P over RT, and moles per liter is the molarity. So in this particular case, what we could do is if we had this reaction, we could actually follow the pressure over time. And by doing so and just using something as simple as the ideal gas law, you could relate that pressure over time to basically the molarity of the gas. In this particular reaction, there is only one gas ever, which is oxygen, and it is a product, which means you will not have pressure until you start to make it, right? So you know it definitely is, start to see the pressure start to rise. You're definitely making, obviously, some oxygen gas molecules in this case, and you would be able to follow that over time. And now by simply just following the pressure over time, you'll be able to figure out how the concentration of oxygen is changing with time. As R is a constant, and if you did this experiment, most likely the temperature would be constant throughout the entire experiment as well. So again, you don't always need some type of reaction where maybe there's a color that you could use for absorbance values in like a spec 20 type experiment. You could do something like this where you follow pressure over time and you could use it to relate back to concentration versus time, especially obviously if it's a gas involved. Any questions on that there? All right, so when we're doing these rate expressions, as we know, whenever we have an equation, the one thing that we always got to kind of take into account is our friend stoichiometry. So not all reactions basically react as a 1 mole to 1 mole relationship. For example, here we get basically 2 moles of A gives us 1 mole of B. So that does also affect the rate of a reaction and how it's basically appearing and disappearing with time. So if we were going to write the rate expressions for this reaction, we would do for our reactants, negative here because it's a reactant. We actually will take 1 over the coefficient. So that is where the 2 comes from. And if you do 1 over the coefficient, what that will do for you is a combination of the stoichiometry together with the kinetics all in one move. You don't have to do it separately. You can, as we'll talk about, do it separately. You could kind of do like a stoichiometry problem first and then do the kinetics part of it. But if you do 1 over the coefficient, it'll basically kind of combo that together for you all in one calculation. And this is still the change in the concentration of A over the change in time. We could also do it for our product here. Once again, no negative. The coefficient on our product is 1, which means basically that's 1 over 1, which is equal to 1. And that's why there's really nothing there. You don't have to write 1 over 1 because it's obviously just going to equal 1 in this case. So in general, if you have a reaction such as this, you could take the rate is equal to minus 1 over A, change the concentration of A over time, equals minus 1 over B, the change in concentration of B over time, equals 1 over C, change the concentration of C over time, and 1 over D, change the concentration of D over time. These are our products, so there's no negatives there. These are our reactants, which do have the negatives. What does this allow you to do? It frankly allows you, if you just know one piece of information, maybe you know the average rate for the reaction, that would allow you to figure out how A is changing with time, how B is changing with time, how C is changing with time, how D is changing with time. If you just knew how D was changing with time, that would allow you to figure out all the rest of it, how C is changing, how B is changing, how A is changing, and how the average rate would be for that reaction. So if you just know really one sort of piece of information about how somebody is changing in a reaction or what the average rate of that reaction is, you could use these relationships to figure out how everybody else is changing. Do you have to use it all together like that? You don't. You could actually just take the 2 things you're interested in. Let's just say we knew something about D, but we want to know something about A. So we could just break that off into the rate is equal to minus 1 over A, the change in the concentration of A over the change in time. We could write a rate expression for our product, which is the rate is equal to 1 over D, the change in the concentration of D over the change in time. So if we did know about D, what that would allow us to do is figure out the average rate for the reaction. And how that helps you with this guy is this number here and this number here are the same number because it's the same rate for that reaction. So if you can figure it out for the first guy, you then will know the rate for the second guy and it should be the same. And you can do something like just solve for that part of it, and you can figure out how A is changing with time. So that's why I said if you just know really one piece of information, it will allow you basically to figure out how everybody else is changing. Any questions on that there? All right, so why don't you write the rate expression for this reaction and see what you come up with. All right, so let's take a look. So we'll start with the rate is equal to our first reactant. We do need a negative because it is a reactant. The coefficient here is 1, so that's basically 1 over 1, which means we don't really need to write it. The change in the concentration of CH4 over the change in time. That will equal our next reactant here, so it's a reactant, so it will be negative. Coefficient here, though, is 2, so that would be 1 over the coefficient, which is 2. The change in the concentration of O2 over the change in time. Now we're heading to our product side, so we do not need the negative. Here the coefficient is 1, which again is 1 over 1, so you don't really need to write it. The change in the concentration of CO2 over the change in time. And lastly here, we have a 2 for the coefficient. That would be 1 over 2 as it's a product. Again, you don't need the negative here. The change in the concentration of H2O over the change in time. Once again, here, if we knew any of the numbers for any of these guys, we could basically figure out how CH4 is changing with time, O2 is disappearing with time, CO2 and water is appearing with time. Any questions on that there? All right, so why don't we try one here with numbers? So see what you come up with. For the reaction given, the concentration of I minus goes from 1 molar to 0.868 molar in the first 10 seconds. What is the average rate? And how is the change in concentration of H plus over time? How is that changing? So let's take a look, see how we work this one here. So we're given some information about I minus here. And we have the initial concentration of it is 1 molar. We also have its final concentration, which is 0.868 molar. And we have basically our time here of 10 seconds. So that could be like your final time, and your initial time would be 0 seconds, obviously. Here we want to calculate the rate, and we also want to calculate how H plus is changing with time. So really, we have information about this guy, and we have information about this guy. So really, those are the two rate expressions we want to kind of write. So if we do it for the first one, the rate is going to equal minus 1 over 3, which is the coefficient here for our I minus. It's negative because it is, again, a reactant. The change in the concentration of I minus over the change in time. We could also write an expression for our H plus here, and that would be the rate is equal to minus, again, because it is a reactant, 1 over the coefficient, which is 2. The change in the concentration of H plus over the change in time. We're obviously going to start with the I minus, since that is the only information we really have in this case. So if we put in our numbers here, the rate will equal negative 1 over 3. Again, we want to take our final concentration, which is 0.868, minus our initial, which is 1 molar. And we do want to do final time minus initial, which is seconds. This right here is going to give me a negative number because it's a reactant. It's decreasing with time, which once again will work well with the negative we got in front to give us our rate as a positive number. So we'll go 0.868 minus 1 divided by 10, also divided by 3 to take into account the stoichiometry here. And we will end up with an average rate of 0.0044. The units here are molarity over seconds, and that would be our average rate for this reaction. So on average, everybody is changing 0.0044 molarity every second. So every second, that is the change in molarity that's happening. First off, any questions on that part of the calculation? How that's going to help us now is we want to relate it to our H plus. So we know that our rate is equal to negative 1 over 2, the change in the concentration of H plus over the change in time. So we just solved for this because it is the same rate. That means we actually want to solve for this whole thing. So that means that basically we have 0.0044 molar seconds equals -1/2 the change in the concentration of H plus over the change in time. We need to actually multiply, since we're looking to solve for this guy, the 2 to the other side, but not just the 2. We also have to take the negative as well. So we got to multiply basically -2 to the other side. And if we do that, that's going to get us there. Not that. That's going to get us there. A negative 0.0088 molar seconds is equal to the change in the concentration of H plus over the change in time. So we see here that on average, everybody is changing 0.0044 molarity per second when you take everybody into account. But we see here the H plus is actually changing twice as fast, right? It's actually decreasing, is what that negative means there. That negative on that answer means that as time goes by, it's losing 0.0088 molarity every second, basically, is what that number means. And again, that's happening because the coefficient is 2, and it's kind of like a 2-to-1 type situation that's occurring here. Question on that calculation there. All right, why don't you try another one here? If you have 2.4 times 10 to the 2 grams of NOBR molar mass, 109.91 grams per mole from the periodic table, it decomposes in a 200 milliliter flask in 5 minutes. Find the average rate of BR2 production here. All right, so let's take a look since we're getting to the end here. If we have 2.4 times 10 to 2 grams of NOBR, decomposes in a 200 milliliter flask at 5 minutes. What is the average rate of BR2 production? So clearly we have some information about NOBR, so we could write our rate expression for it. And that's going to be negative because it's a reactant. 1 over the coefficient, which give us 1/2. Change in the concentration of NOBR over time. We also are going to try to relate it here to BR2, which is the rate is equal to, here the coefficient is 1, so we don't need it. We also do not need a negative because it's a product. Change in concentration of BR2 over the change in time. So here we really need the molarity. So we don't have the molarity given to us, but we do have grams of molar mass, which means we could get moles from that. And we do have the volume, which means we could also get molarity. So that's what I'm going to do. I'm going to take the 2.4 times 10 to the 2 grams of NOBR. I'm going to use the molar mass from the periodic table that was given to us of 109.91 grams per mole. And that will get me 2.4 to the 2 divided by 109.91. I'll call it 2.1836 moles of NOBR. We have basically 200 milliliters, which if we convert to liters by divided by 1,000, will give us 0.2 liters. So we can take our moles there to get the molarity here of our NOBR. And that would be our 2.1836 moles divided by 0.2 liters. And that's going to get us there. And we'll go 10.92 molar. That is basically the amount of NOBR that's going to decompose, basically the molarity of it. Now, our time is in minutes. Ultimately, we do want it in seconds. So I'm going to do a conversion from minutes to seconds just to put everything in the right units. So we got 5 minutes, and I think a minute is 60 seconds we'll go with. Is that 300 seconds, I believe, if I'm not mistaken on that. So we have everything we need now to go into this rate expression, -1/2. We are going to do negative 10.92 molar. The reason we're doing negative on that case is it should be a reactant, which means it should be decreasing with time, which means if you technically did final minus initial, you would end up with a negative number. So again, the rate needs to be a positive number And we're just has to, in this case, kind of put the negative in there to make sure we get it. That way, again, the negative here and the negative here will turn this guy into a positive number. And that would get us that divided by 300 minus 0, basically, divided by 2. Going to give us a rate here of 0.0181 molar seconds. Actually, 2. I could do the rounding there. So 0.0182 molarity over seconds. Now we can relate that to our BR2, because that is equal to the change in concentration of BR2 over the change in time, actually equals the rate, which means not much to do there except multiply it by 1. And we will actually have how the BR2 here is increasing with time. The importance of the negative and positive is BR2 is a product. So here, when we're talking about how BR2 is changing with time, we do need that positive number, which is what we ended up with. So again, you just kind of watch the negative and positive signs. If you end up with, like we did previously for our reactant, we will end up with a negative number for how it's decreasing with time. Here with a positive number, that means that it's increasing with time at that rate. Question on that there. Now, just to finish this one here, as I mentioned before, when you do 1 over the coefficient, that does take the stoichiometry into account for you. But if you wanted to do just a regular stoichiometry problem first and then kind of put the kinetics part of it, you could. You could take the moles of the NOBR that we calculated, and you could just do a mole-to-mole relationship from the equation, and we see again it is a 2 mole of NOBR to 1 mole of BR2, and that will get you your conversion over to BR2, which is 1.0918 moles of BR2. You then can turn that into molarity by dividing by the volume, 0.2 liters. And now that will give you 5.459 molarity. Kinetics, though, is also about time. And what you could then do is divide that molarity by the time, which was 300 seconds. And lo and behold, you will end up with the same thing as we got above. So if you want to just do a regular stoichiometry problem and then go into the kinetics part, divide by the time and do that type of part, you can. Or if you do, like we see here, 1 over the coefficient, that does it for you. Why is it 1 over the coefficient? Because you can see right here in the mole-to-mole relationship, 1 over 2. And that's what takes into account basically for it, is why we do 1 over the coefficient there. Any questions on that there? All right, we're wrapping up there for today.